Okay. Let's get started. So 5.3 and 5.4, that's a lot of the heavy lifting for theory in these chapters. From here on out, we're just going to be using stuff we already knew in those things, learning some tricks to take some integrals, and then some applications of integrals. Today we're just going to be like looking at tricks for calculating integrals. Because notice that an integral is much harder to calculate than a derivative. I can put almost anything up here and you'll know how to calculate the derivative of that thing. You might get confused in the algebra somewhere along the way, but you in theory know how to take the derivative. Right? If I ask you to take the derivative of something like cosine squared of theta, you know, use the product rule. The derivative of the first multiplied by the second plus the derivative of the second multiplied by the first, and you know how to take the derivative of that. But when I ask you to do something like calculate an integral of this thing, that's a much harder question for you to answer. What is the thing whose derivative is cosine squared?
Yeah, what do you do with the square?
Yeah, how do we handle these types of things? So we know how to take integrals of polynomials. So something like 4x cubed plus 3x squared, stuff like that. Mm-hmm. We know how to take integrals of things that are of trig functions where we already know it's a derivative of something. So if I just had a cosine there, you know how to take the derivative. Right? Or you know how to take the integral. If it's just cosine, what's the integral of cosine?
Negative sine.
Let's see. The integral, not the derivative.
Oh, yeah.
You take the derivative of that, you get that. So you take the integral of that, you get that. Mm-hmm. But then suddenly when we put the squared there, it gets a lot harder. And now we're not sure what to do.
So we're going to be working with stuff like that?
Well, kind of. The point is, I want to show you how limited your ability to calculate an integral is so far. You can almost calculate the integral of nothing. Yeah. You can do polynomials, and you can do it if I show you like a trig function that you already know exactly what's the derivative of.
Yeah.
Something a little bit complex like that, and you're already at a loss. You see our problem? Mm-hmm. Or if I were to give you something like the square root of x squared plus 1 over 2x. You know how to take a derivative of something that looks like that real easy. Mm-hmm. That would be the quotient rule. How do we get the integral of something like that? That's a much harder question.
Yeah.
What is that the derivative of? That's much harder to answer. So we'll learn how to do, in this section, we're going to learn how to deal with stuff like this.
Okay.
And maybe we'll just do this one, since, well, no reason not to. So the trick is always to try and get this in an integral of some function of u with respect to u that you do know how to integrate. So we need to do substitutions with this thing to try and make it look like something that we do know how to integrate, somehow make it a polynomial. So the method that we're learning today is called U-substitution. U-substitution.
Okay.
And the idea behind U-substitution is let me just solve one, and then we'll talk about what that is. So here I'm going to let u equal x squared plus 1. And let's say that I wanted the integral of this thing from 2 to 4. Put some bounds on there. You with me? Mm-hmm. So I want the area under that function from 0 to 4. Did I say 2 to 4? Yeah. Okay. So if I let u equal x squared plus 1, right? Then what is my du equal to?
The root of u over 2x.
U is equal to that. What is du?
2x.
2x dx. If we think about it the same way we did differentials.
Okay.
So rather than finding du dx, then if we just find du by itself, the dx is over here. You with me? Mm-hmm. Okay. So notice that from this equation, what does dx equal?
Du over 2x.
Du over 2x. Oh. this integral, I was thinking backwards in my head when I said it. This is why I should just do exercises from a book. Let's pretend that this was the square root of x squared plus 1 times 2x dx. You with me?
Okay.
Okay, still going to do the same substitution. U is equal to x squared plus 1. That other one I would have had to use a trig substitution, I think, which is a more complex idea. So u equal to that, still du is the same thing, should erase all this. It's still 2x dx, right?
Yeah.
Now I'm going to do substitute values in for this integral. I know that x squared plus 1 is the same thing as u. So that's going to become a u. And this 2x dx is just going to become du.
Okay.
So this is equal to, look, there's no rule that says I can't just create a new function u that's equal to x squared plus 1, right?
Mm-hmm.
I can let anything equal anything I want along the way. I'm just relabeling those things u. And if I call that thing u, then I'm calling that thing du. And this is all perfectly legal, right? There's nothing, okay. Just want to make sure that you see that we're not breaking any rules of math here.
Okay.
So this then becomes the square root of u, or u to the 1/2, right?
Mm-hmm.
Du.
Why is it square root? Or, yeah.
Huh?
How did you get to the root of the root?
X squared plus 1 is the same thing as u. So we have square root of u. You with me?
Yeah.
Everything good?
Yeah.
Now the one thing that's still weird here is, here we were finding the area under this function of x from 0 to 4.
Okay.
Now we have a function of u. Now really, this is the exact same thing as this, right? They're equal.
Is that still supposed to be from 0 to 4?
Well, that's the question. What should this be from now? Because now we have a new function in terms of u, rather than in terms of x.
But it's saying the same thing.
It's saying the same thing, but now, if you want to think about this as a u function, we change. We now have a new picture. Our x-axis is now a u-axis. Here's our u. And for each u, here's f of u that we plot here. So we took our function and we went and we stuck it on here. And now on this new graph, where do I need to find the area to get the same area as the area that we would have gotten over here? How did we change the bounds?
Why isn't u just a placeholder?
We could use u as a placeholder, and we'll see that. I'm going to do it one way, then the other way.
Okay.
So we'll see both. So we need to change our bounds. When x is 0, what is u?
1.
1. When x is 4, what is u?
17.
17. So now, finding the area under this curve from 0 to 4 is the same as finding the area under this curve from 1 to 17.
Okay.
Because if x goes from 0 to 4, u goes from 1 to 17.
That makes sense, I
Right?
guess. Yeah.
Okay. So now here's our new integral. And how easy is that integral?
Pretty easy.
It's stupid easy, right? This is equal to integrate u.
2/3 times u.
2/3
3
u
over
to the 3/2, right?
Yeah.
Evaluated from 1 to 17. Now, since I came up with the numbers, the math's not going to come out nice.
Okay.
But, so it's equal to 2/3 times 17 to the 3/2 minus 1, whatever that is.
Okay.
Right? Now say we didn't want to change the bounds. So, let's say we said this was equal to and we left our bounds off. And we were just thinking about it in terms of substitution that we need to, what did you say before?
Placeholder.
Saying we're treating it as a placeholder. So let's say we had this was u to the 1/2 du, and we know how to calculate that thing's integral. This is, once again, it's still 2/3 u to the 3/2, right?
Yeah.
But this is equal to 2/3 x squared plus 1 to the 3/2, right?
Yeah.
And now we need to evaluate this from 0 to 4. And this is equal to 2/3 times, when you plug in the 4, 16 plus 1 is 17, 17 to the 3/2 minus, we plug in 0, 1. So it's the exact same thing.
So it doesn't matter which way.
No, it doesn't matter. So you can view u as just a placeholder and go back and substitute back in.
Okay.
Or you can change your bounds of integration. It does the same thing. Because changing your bounds of integration is the exact same thing as what you're doing here when you plug in those numbers.
That makes sense. Do you solve all these complex problems this way?
No, there are tons of rules for how to solve integrals. Almost all of Calculus 2 is dedicated to methods for solving integrals. Solving derivatives, super easy, absurdly easy. Solving integrals, absurdly hard.
Okay.
So you're happy when you have to calculate a derivative. You're very sad when you have to calculate an integral. And a lot of very simple looking integrals, you can't even express the result using mathematical notation that we have.
How does that work?
How does that work? It's not some sort of polynomial. It's not some sort of trig function. It's not some sort of rational function. We can't express it with square roots. It's not some x to some power. It's not exponential. But it is something. We just haven't developed any notation for what that thing is. And so sometimes we say the integral of this function is the integral of this function. And we have notation for the integral of that function.
What the heck?
You can't represent it with some simple algebraic expression, what the integral is. And very simple looking things can end up being that way. I think something like this is like that. X cubed minus 1, I think is one of them, the integral of that. So you can have very simple looking things that you can't calculate the integral of. Even though there is area under a curve for that thing. So we can calculate the area under a curve approximately.
Yeah.
We know how to approximate it, but there isn't some nice equation that represents the integral of that thing.
Why don't you just use a placeholder rule?
You can't just use the placeholder rule every time. Let's go back to the equation that we had before and try using just placeholder rule when I change it a little bit. Let's say we were supposed to calculate the integral of x squared minus 1 dx. Now you don't know how to calculate this integral yet. You'll learn in Calc 2 how to calculate this integral. But let's be a little bit naive and try and use the substitution rule. Okay, so u is equal to x squared minus 1, right?
Mm-hmm.
So du is equal to 2x dx.
Okay.
So dx is equal to du over 2x, right?
Yeah.
So let's do our substitutions. So this is equal to the integral of, we replace this with the square root of u, right?
Mm-hmm.
Times, and we replace dx with du over 2x. Uh-oh, we still have an x in there. Now you can say, oh, well, we can figure out x from this equation, right?
Yeah.
So I know x squared is equal to u plus 1. So that means that x is equal to the square root of u plus 1, plus or minus. We'll just keep positive for now. So now, this is equal to the integral of the square root. We have square root top and bottom, so we can do it all in one big square root of u over 2u plus 2, because of that 2x du. Okay, is that any easier to calculate than where you started?
Might be.
Or does it feel like we're just moving backwards? This is not the way to solve this. So I gave you a very special one that made so that you could solve it. I made sure that there was a 2x on the outside of this thing. So that when you replaced your dx with a du, you also got rid of those pesky extra x's. Because now when it's like this, we can calculate the integral real easy. But if I get rid of that 2x, okay, now this integral just got really hard.
Yeah.
Yeah.
So it needs to be in very special forms for the integral to suddenly be easy on how to do it. Make sense?
Mm-hmm.
So in U substitution, it might be misleading, all the problems that the author's going to give you now, make you think like, oh, you can just use this all the time. No, it's very limited. A lot of these are very limited. And it works because problems were picked to give you ones that it works with. And so, yeah, a lot of Calc 2 is just flat out, You're given a whole bunch of integrals to solve, and you got to figure out which method to use to solve them. One method is U substitution. But there's lots of other methods. Good? This is just the simplest one. Okay, so now let's start going through the example problems and start calculating their integrals. Because this is going to be a chapter where I'm not really teaching you stuff. You just need to see a lot of examples and get a feel for what we're doing.
Okay.
Because you already know what we're doing, U substitution, to try and make it something we can integrate. So let's see. It says calculate the integral of x cubed plus x to the 5 times 3x squared plus 1 dx. Now this is actually an easy integral because even though the algebra gets hairy, the integral itself is easy, is what I mean. Because you could always expand that out, even though it blows up and it has a ton of terms, and multiply by that, which blows it up and it has a ton of terms, but you could solve it, right?
But you don't want to do it that way.
You don't want to do it that way. It's stupid to do it that way. But the point is, U substitution also helps us with integrals that we already know how to solve. So not only does it teach us how to solve integrals that we didn't know how to solve, it can also help us with integrals even though we know how to solve this without U substitution. U substitution is going to make this a lot easier. Does that make sense what I'm saying?
Yeah.
Okay, so U substitution, we're always trying to see, can I see some part of this and another, can I split this thing into two, where one I can view as a function of U and the other one I can think about as du. I'm looking for a U and a du in this thing that I can substitute to get rid of all my x's.
Yeah. Let u equal x cubed plus x.
Yeah, so if we let U equal x cubed plus x, then what's du?
3x plus 1.
3x squared plus 1.
Yeah.
Dx. Don't forget the dx there. Right? Perfect. Notice that when we do that substitution, it gets rid of all our x's. That's what we're out to do.
Getting rid of all the x's?
Replacing all our x's so all we have are u's in there.
I see.
Because we can't integrate with respect to u if we still have an x in there.
So the 5 doesn't matter
Nope.
if it... Okay.
No, so exactly what you did was perfect. So this is still the integral. I don't know if there are bounds on this. There's none. So we're calculating an indefinite integral, so you gotta put plus c at the end. Anyways, so now we can rewrite this as u to the 5 times du.
Okay.
You see how simple that was?
Yeah.
And now, what is this?
U to the 6 divided by 6.
U to the 6 over 6, which is equal to, when you're calculating an indefinite integral, always go back to your x's. Since your definite integral, you're just spitting out a number, then it doesn't matter if you go back to the x's or not, because the number is the same. If you're doing an indefinite integral, you cannot leave it like this. You can't leave it like this plus c. You will not get credit if you leave it that way. You need to go back to your x's. This is 3x squared plus 1 to the 6 over 6.
No,
that's du.
Oh, thank you. X cubed plus x. There we go, right? And so it turns out the derivative of this thing is that.
How does that make it easier to calculate?
Because
Then multiplying this out,
I mean,
I want you to just, let's just do, for a second, a plus b cubed, and see how that blows up.
can't you just use the chain rule?
When we multiply this out,
Oh, that's right. I was thinking.
I'm talking about algebra, not derivative. I'm talking about a plus b times a plus b times a plus b.
Yeah.
And what does that equal to? If you don't know the trick, then this is hard. Well, not hard, but kind of annoying. So this is the same thing as a plus b times a plus b times a plus b, which is equal to, okay, let's do this one first. We need a times a gives me a squared. Then we have a times b gives me a plus ab. Then we have b times a gives me a plus ab. Then we have b times b gives me a plus b squared. All times a plus b. And now I need to take each of those and multiply by a, each of those multiply by b.
Okay.
And then that gives me even more terms. And then if I did that 2 more times, oh my goodness, it's blowing up. So typically we avoid expanding things out like that. Now if you remember Pascal's triangle, then it's not so bad.
Didn't we like prove that? In discrete?
We proved things about it.
Okay.
We proved the formula that you can use to expand these things out. We'll start with 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Let's see, this is to 0, to the 1, to the 2, to the 3, to the 4, now to the 5. Oops,
10.
that's 10. So now when I write this thing out, it's going to be, and then I also need to set, doesn't matter. This will turn to electrons on. Doesn't matter, doesn't matter, doesn't matter. That's how you get your coefficients, but then you need them descending powers. Anyways, let's focus on calculating integrals. Okay, next one. Next one's a nice simple integral. We need to calculate the square root of 2x plus 1 dx. What should we let our u be?
2x plus 1.
Yeah, so even if you don't see where the derivative is in the sink, try and just throw out a guess for u. Sometimes something's begging to be u so far. So even if you can't see all the way down the road, it kind of makes sense. U should probably be 2x plus 1. So we have, if u is equal to 2x plus 1, what is du equal to?
2 dx.
2 dx. So what does dx equal?
Du over 2.
Du over 2.
Oh, but you got rid of your x.
But you got rid, there you go. So all that matters is you get rid of your x. You might be throwing in constants, getting rid of constants. Just make sure you get rid of the x's. So you saw how you couldn't quite see where this was going to begin with, but then it suddenly jumped out to you when you solved for dx. So that's very much the case sometimes. You can't see exactly where it is you're going, but you have a feel for where you should go, so you go exploring. And that's very often going to be the case.
Okay.
All right. So anyway, so this is equal to the integral of u to the 1/2 times du over 2. Right?
Mm-hmm.
Okay. So now we can calculate that integral. The 1/2 is just a constant, so we could have pulled that out. Probably should have done that. But what's the integral of u to the 1/2?
2 over 3u, 3 over 2.
So we have 2 over 3 u to the
3 over 2.
3 over 2, and we still have our 1/2 in there, right?
Oh, so it just turns into a coefficient?
Yeah. Not,
Okay.
du over 2 is the same thing as 1/2 du.
Yeah. Okay,
Okay.
that makes sense.
Plus our constant, which is equal to 2's go out, so we're left with u to the 3/2 over 3 plus c.
Yep.
Okay.
2's go out.
Mm-hmm.
This 2 with that 2.
Oh.
That's what I mean. Okay. Let's do another one. One that looks complicated, but isn't. So we're looking for the integral of secant squared of 5x plus 1 times 5 dx.
Well, make u be 5x plus 1.
So if we make u equal to 5x plus 1, then du is equal to
5 dx.
5 dx. And so this is now equal to the integral of secant squared of u times du. Right? Which is equal to tangent of u plus c, which is equal to tangent of 5x plus 1 plus c.
Yep.
Alright, let's Let's do another one. Calculate the integral of cosine of 7 theta plus 3 d theta.
Let's go with u for 7 theta plus 3.
U equals 7 theta plus 3. du is equal to
7.
7 d theta.
D
Right?
theta, yep.
Substitute our d theta, so d theta is equal to du over 7.
Okay.
Okay, so this is equal to the integral of cosine of u times du over 7. Right?
Mm-hmm.
The over 7, that's just 1/7, that's a constant, we can pull that all the way out. So, what's the integral of cosine of u?
Sine of u.
So this is 1/7, hold the 1/7 all the way out. 1/7 sine of u plus constant, which is equal to, we'll just do sine of
7 theta
7
plus
theta plus
3.
3 all over 7 plus the constant.
Okay.
Make sense?
Mm-hmm.
Feel like you could do these?
Yeah.
I mean, you got your basic unit, right? I'm just writing.
Do we get into other complex things? Or is it just substitution?
All of this section is U substitution. 5.5 is U substitution.
Okay.
That's why I said it's not really teaching you anything new. It's just one of those ones where this is a method you use so much, you just gotta get comfortable doing it. It's kind of like I'm giving you a big times table sheet.
Why is it called indefinite integrals then?
5.5?
Because we're not doing from like
Oh,
0 to 4,
Indefinite integrals with the U substitution. Indefinite integrals, we're back to this. You've already seen indefinite integrals.
Do you always want to add a c for the answer of an indefinite integral?
That is what an indefinite integral is, right?
What does it mean for it to be indefinite?
Undefined.
Not undefined, but we don't know exactly what it is. Right?
Yeah.
Indefinite. So yeah, plus C, plus some term we don't know. Some constant. Let's see. Which one were we on? We did that one. We're on this one. Okay. This one, we have x squared times cosine of x cubed dx. Okay, so what should we let our u be?
X cubed.
So we let u be x cubed, du is equal to what?
2x cubed.
Try again.
3x squared.
dx.
Dx. Remember the dx, because you're ultimately substituting the dx in here. So dx is equal to what?
d over 3x squared.
Right?
Yeah.
But you have an x squared.
Well, that cancels out the x squared in the denominator.
Yeah, however you want to think about it. We
Oh.
could have grouped the x squared over here. So there's two ways that we can think about this. I personally just like to solve for dx and plug it in, and then let cancel out. That's what I personally like. Another way that they often teach it, the way the author even likes to do it, is he says, so the way that we're going to rewrite this is, kind of ignore this step and just look at this. We know that du needs to be 3x squared dx, so let's force that to show up here.
Okay.
So if I'm going to multiply this thing by 3, I need to divide it by 3, so we do 1/3 times the integral of cosine of x cubed, and then I can do 3x squared dx. So 1 and 3 is just 1, so I didn't change it.
Mm-hmm.
I move the x squared over here, and then do the substitution. So now I know that this is du, and this is cosine of u. So this is equal to the cosine of u times du. So that's why the author's going to do it in the book.
Don't forget the 1/3.
Thank you. I personally just solve for dx and substituted it. Both work.
Okay.
So whatever you like more, stick with it. This is equal to, now we know how to calculate this. What is it?
Sine of u.
Sine of u, but u, we don't need a,
X cubed over 3. Let's see.
right?
Yeah.
Yep.
Another one, right? These are easy, we can do this all day.
Yeah.
Good. So that's essentially what your test is going to be.
Just these?
Just a page of integrals. Just solve them all. I'll just go find some integral sheet online and we'll make that your test.
Okay, I don't mind.
Okay. Makes my job easy. I have to write tests. X times the square root of 2x plus 1. Did I already do that one? No, example 6. Okay. What do you think we should let our u equal?
2x plus 1.
So if we do u is equal to 2x plus 1, then our du is equal to
2 dx.
2 dx. So I'm going to get rid of all of our,
No.
let's keep working with it and see if we can do some exploring and figure it out.
Okay.
So we can still say dx then is equal to du over 2. Let's plug in that and see where that gets us. So now we've got the integral. Don't bail out so fast just because things aren't working. You're clever. You might be able to figure something out. You might be able to see something. Right? That's where we're at so far.
Yeah.
What can we do with that x? Is there any way to get rid of it?
Put another u in there.
How? Ah.
Just spitball.
Can we find x in terms of u?
Yeah, we can.
So what is x equal to?
X is equal to u over 2.
U minus 1 over 2. Yeah, minus the 1 first and divide.
Isn't it minus u?
No. Minus 1 from both sides.
Yeah.
Divide both sides by 2.
Oh, you're right.
Okay, so this is equal to the integral of, we have, I may write this as 2 separate fractions. U over 2 minus 1/2 times u to the 1/2 du.
Alright.
Where'd your du over 2 go?
Oh, thank you. Let's get that 2. I'm going to put the 2 here. We got 4 and a 4. Shove it in there so I just have all my constants in one place. You good with what I did there though?
Yeah?
Okay, let's multiply it out. This is equal to the integral of u times u to the 1/2 is what?
U to 3 over 2? No. Is it?
Yeah, u to the 3/2. When you multiply terms, you add exponents. 1 plus 1/2 is
Oh.
3/2 over 4 minus u to the 1/2 over 4 du. Now remember, we learned yesterday that the integral of a difference is the difference of the integrals. So this is the same thing as the integral of u to the 3/2 over 4.
You could also pull out 1.
Yeah, let's pull out 1/4. 1/4 u to the 3/2 du minus 1/4 times the integral of u to the 1/2 du. You know how to calculate those?
Yeah.
So.
Yeah, nice and easy. So this is equal to integral of u to the 3/2 is
2 over 5 times u to the 5/2.
and we still have our 1/4.
Yeah.
plus some constant, we'll call it C1, minus
One
Oh.
over.
2 over 3 to the u to the 3 over 2 times 1/4 plus C2.
Can't you just do 1C? Why do
Yeah, you can. Since it's a constant, it's a constant, it's a constant. A constant plus a constant, or if you say, oh, that should have been minus, a constant minus constant is still a constant.
Yeah.
So when it's all said and done, even if you're doing multiple indefinite integrals, you just need 1 plus c at the end and you're fine.
Okay.
So we can always rewrite this as, let's cancel out here. So we have u to the 5/2 over, when we do that, we're going to have 10 in the denominator, minus u to the 3/2 over 6 plus some constant c.
And that's it?
That's it.
Yeah, that makes sense.
Oh, no, that's not it. Obviously, we don't leave our u's in there.
Oh.
This is not the antiderivative of this, right?
Yep.
If you take the derivative of this, you do not get this.
Okay.
Okay, so we got one more step, which is going to be, it's 2x plus 1 to the 5/2 to the 5/2 over 10 minus 2x plus 1 to 3/2 over
6.
6 plus c. Maybe they're going to factor out a 3/2. I don't know if they're going to do that. Let's see, when he writes his answer, does he factor out? No, he leaves it like that. Okay, so we'll leave it like that.
How do you factor out 3/2?
The 2x plus 1 to the 3/2. We could get a common denominator, then factor it out, and then combine one of our terms. But
Oh.
either there, I'm not going to worry about it. It's fine like that. Okay. So far these have been pretty straightforward, right?
Yeah.
Now, we're going to do one a little bit ugly. One that's not so straightforward. Okay, and we already saw this at the beginning. How do we do the integral of sine squared of x dx? Something like that. Yeah, he does that. So now we are once again stuck. We know how to work with just a sine. We don't know how to work with a sine squared.
Okay.
We know how to work with just a cosine. We don't know how to work with a cosine squared. So you're going to have to go back to your trig identities and see if there's some way that we can rewrite that so that we can get rid of that squared.
Okay.
Do you have your trig identities written?
Yeah.
Somewhere. For integrals? Or just-
No. For sine squared of x. What's another way that we could write sine squared of x? And that doesn't have any squares in it.
Sine squared.
Your half angle identities. You might just have sine of x equals a half angle identity. I'm not sure how you have that. Somewhere on there you have either this. Sine of x is equal to the square root of, let's see, with cosine is a plus or minus. Or with sine is a plus or minus, it's minus. 1 minus cosine of 2x all over 2. You either have that written on your paper somewhere.
I have it as
Yeah, that's right.
sine of theta over 2.
Sine of theta over 2. But
Oh,
I was
okay,
trying to
watch.
square.
X equal theta over 2. Right? Now let's rewrite this. That becomes theta over 2. And this becomes theta. All that matters is the inside one is double what the outside one is. Doesn't matter what color. You with me?
yeah.
So I'm going to go back to putting this as an x. And this is a 2x. So sine squared of x then is equal to that.
Do we have that written down?
I just squared both sides.
Oh, sorry.
Yeah.
Okay.
This is the way the author wrote the identity.
Gotcha.
Anyway, it's just trig identity. So that's going to be our substitution. And if it's cosine squared, we use 1 plus. That's the only difference. So we now know how to work with a sine and a sine squared. So this is the same thing as the integral of, I'm going to write this as 2 separate fractions, 1/2 minus cosine of 2x over 2
Didn't you say it had to be plus?
dx. Plus when this is cosine, minus when it's sine.
Yep.
Yeah, I always get a little bit confused which is which, but obviously I have the author's work right here so I can see which identity keys.
But you still have x's.
You still have x's. There's nothing particularly wrong with x's. So using that, let's go ahead and split this up into 2 integrals really quick. So this is the integral of 1/2 dx minus the integral, let's pull the 1/2 out of each one actually. So this is 1/2 the integral of dx minus 1/2 the integral of cosine of 2x dx.
Oh, we know how to do that.
Almost. Or maybe you do. I don't know. So first off, let's do this one. What's that one equal to?
What is that equal to? Just 1/2?
What is the integral of dx?
1/2 x.
1/2 x.
I'm confused.
If u equals x, what does du equal?
Dx.
Dx. So the derivative of x is dx.
Yeah, but yeah, that
So the integral of dx is x. The integral of u is u. The integral of dx is just x.
So it's x over 2.
Oh, so the whole thing's x over 2.
Oh. You
Yes.
said 1 over 2x.
1/2 x.
Good.
Oh, did I get confused? I probably got confused.
Okay, let's just write it and then we'll
Okay.
be on the same page. X over 2.
Yeah.
That's what we're saying it is. Okay, that makes sense to everyone. Okay. Minus. Now we know how to calculate the integral of cosine of x. We don't know how to do cosine of 2x.
Just make u 2x.
Do you properly?
So yeah, we can do u is equal to 2x. And what does du equal?
2 dx.
And so dx is going to equal du over 2.
Mm-hmm.
So that's going to be our substitution.
Yeah, that's not that.
So this is minus, I'm going to take this 1/2 and this 1/2 all together and just put the 1/4 here. 1/4 the integral of cosine of u du, right?
Mm-hmm.
And now we can calculate that, so this is all equal to x over 2 minus 1/4. What's the integral of cosine of u?
Sorry.
Sine, and we'll say sine of u plus constant. Anything weird? Any questions?
No.
Oh, he has a part A, B, and C. It's looking at the bottom of the problem. I'm like, well, we got a way different answer than him. Okay, no, we got the exact same answer. X, sine of 2x over 4. Ooh, he has a... No, he has a minus. Jeez. Keep looking at the right side. We did it. Okay,
Okay.
so next we're going to do cosine.
Cosine squared?
Yes. This marker that's better.
It's the same thing you said, 1 plus.
So this was going to be cosine squared of x. So this is going to be the integral of, this time we're going to have 1 plus cosine of 2x all over 2 dx, which is equal to the integral of, we can go ahead and let,
We'll split it apart into the 1/2.
yeah, we can split it apart. Pull the 1/2 out, integrate it, and we get x over 2.
Okay.
Good with that?
Mm-hmm.
Plus the integral now, and maybe you'll be okay with me writing this, plus the integral of 1/2 cosine of 2x times 2 dx.
Times 2.
So here's, I multiply it by 1. So that didn't change anything, right?
You have cosine
We
of
have
2x
cosine
over
of 2x over 2.
Yeah.
Oh, thank you. So I need a 4 here.
Yeah,
There
that
we go.
makes sense.
Now I can change it. Good? Okay. So now if u is equal to 2x, then du is equal to 2 dx, which is right there. So this is cosine of u du. So we can integrate that. So this is going to be x over 2 plus, when we integrate this, we're going to get sine of 2x, sine of u over 4 plus c. Good?
Yes, sir.
Next one he wants to calculate. The next one he wants to calculate is the integral of 1 minus 2 sine squared and we're going to have that multiplied by sine of 2x. Okay. Ooh, that should be an x there. Can't have betas and x's. Okay, so this one is already a little bit of a nightmare, right?
Yeah.
A little bit of a nightmare because first off, we have a sine of 2x in one place, and another place we just have a sine of x. Now that is begging for me to come up with a way, let me make sure I wrote that right. 2 sine squared of x, sine of 2x. Okay, I think we're good. So that is begging me to rewrite this somehow as a trig function that has a 2x in it.
What if we made it x over 2?
I need the inside part of my functions to be the same.
Yeah.
Why?
If I do a u substitution, if I do u is going to equal something like sine of 2x, then my du is going to be 2 cosine of 2x. And they're going to have the same inside part. So whatever I choose to be my u and my du here, I'm going to need them to have the same inside part to the trig function, otherwise we're in trouble. So when you got trig functions that you need to integrate, almost always you need to either rewrite this one so that it's somehow just sine of an x function and get rid of the 2x using your trig identities, or add the 2x to the expression here.
Okay.
Okay.
We're going to go the add the 2x route. Kind of begging for it. Okay, so we need to mess with this until it gets into something that we know we can rewrite with the 2x in it. Notice that when we did cosine squared, we could get a 2x in there. So maybe I can get this into a cosine squared somehow or a sine squared somehow. Maybe. You with me?
Yeah.
So, 1, what's our trig identity with 1? What do we know equals 1?
It's cosine squared plus sine squared.
Cosine squared. We're talking about x here. Plus sine squared. That's why I always think when I see trig identities and I see a 1, I keep that in mind. So, we're just playing. Let's play it.
Okay.
So maybe if I do that substitution there, what would I get? So if I substitute that in for 1, then I have that minus 2 sine squared of x. What does that give me? That gives me cosine squared of x minus sine squared of x.
Yeah.
Right? Now, isn't that a trig identity? Look on your table. Do I need to Google trig identities?
It's cosine 2x.
Cosine of 2x.
Yeah.
Okay.
So, we can rewrite this as the integral of cosine of 2x times sine of 2x dx. Now, what should I let my u be?
2x.
No, nice try, but that's not going to get us anywhere. Our problem is that we have both a sine and a cosine in there.
Yeah. So why not making u 2x? Why doesn't that work?
Well, it doesn't get us any further because then I'll have cosine of u times sine of u. I don't know how to integrate a cosine times a sine. So guess again.
Just make u cosine of 2x then.
Yeah, you can make it equal cosine of 2x, that would work. The easier one is going to be sine of 2x.
Okay.
But what you said would work. This just happens to be easier. If u equals sine of 2x, what does du equal?
Negative cosine.
No,
Cosine.
derivative. Just cosine. So cosine of 2x, but we need chain rule, so times 2. So 2 times cosine of 2x dx.
That's right.
That's our du, right?
Mm-hmm.
So dx is equal to du over 2 times cosine of 2x, right?
Well, that
So when I
cancels out.
substitute, it gets rid of the cosine of 2x, leaving a 1/2 remainder. So this is equal to, writing the 1/2 first, 1/2 the integral of u du.
Okay.
Okay, now we know how to work with that.
Yeah.
So this is going to be, tell me what it is,
Just u squared over 2.
u squared over
4.
plus c, but now we need to get back in terms of x, so what is it?
Well, what's
squared
x?
Or sine?
Yeah. Sine of 2x squared.
Sine squared of 2x over 4 plus c. Okay?
Okay.
Yeah.
That was a good one. More examples. Try another marker here. Neither of those black ones are great. We need blue. So our next one, we are calculating the integral of 2z over the cubed root of z squared plus 1. The cubed root of z squared plus 1 dz. Okay?
Okay.
Now, note, there's not always just one u substitution that works. Typically, there's lots of u substitutions that work. On the last one, we did a u substitution for sine of 2x. We could have used cosine of 2x and it would have worked. So just keep in mind, there isn't the one right way to do it. So I don't know if you guys are at one point doing homework together and you see it one way, you see it another way. That could be perfectly valid.
Okay.
So don't think you're finding the one u that works. You're just looking for a u that works. Okay, so what do you think our u should be in this?
Z squared plus 1.
Yeah, that looks like a pretty natural one. Z squared plus 1. So then du is equal to
2z. Dx. I mean dz.
dz. Wonderful. 2z dz, we see that that's exactly our numerator. So this is equal to the integral of u to the negative 1/3 du. Was that too much?
No.
The denominator, we have u to the 1/3 in the denominator, but we're going to bring it to the numerator, so it makes it negative 1/3.
But where'd the 2z go?
Du is equal to 2z dz. So 2z dz is du, and then u to the 1/3 in the denominator is the same thing as u to the negative 1/3 in the numerator. Good?
Mm-hmm.
Now we know how to integrate that. What is it?
U to the, 3 over 2
3 halves,
times u to the 2/3.
which is equal to
Z squared plus 1.
there it is. So even though that thing looked a little bit convoluted, like, maybe we're gonna get stuck, nope, turns out we were fine.
Yeah, that was pretty straightforward.
Okay. Now, I guess that the next section is when we start doing use substitutions with definite integrals. Oops. So going to the next section now. Now we're going to be doing use substitutions with definite integrals where you're going to have to change your bounds of integration or back substitute, whichever one you want to do. Like we did with the first problem we did today.
Okay.
So let's see an example of it. Let's see if we can find a marker slightly better. The orange doesn't show up well. Maybe green.
The blue wasn't bad.
It got bad pretty quick though there at the end.
Oh.
So -1 to 1. Does that show up okay?
Mm-hmm.
For distance? Sometimes the light, I can't tell unless I back up. So this is 3x squared times the square root of x cubed plus 1. Okay, what should our u be?
X plus 1. Yep.
X cubed plus 1. So du is equal to 3x squared dx. So we see those two together give me my du. So I have u to the 1/2 du, right? So this is equal to the integral of u to the 1/2 du.
From -1 to 1.
Now, we have a choice.
Oh, that's right.
Either we're going to end up back substituting back to x's and then plug in -1 to 1, or we change our bounds of integration. Doesn't matter which way you do it, but you have to do one or the other. I cannot put -1 to 1 here. That's the only wrong answer.
That makes sense.
Okay, so I can either leave those off, noting to myself, I need to go back to x's before I can plug it in, or I can change my bounds of integration. And I can say, when x is -1, what's u?
U is 0.
And when x is 1, what's u?
2.
2. So as x varies from -1 to 1, that's the same as u varying from 0 to 2.
Okay.
And now we can continue on our merry way. So this is 2/3 u to the 3/2 evaluated from 0 to 2, which is equal to, when we plug in 2, what do we get?
What's 2 to the 3/2?
What's 2 to the 3/2? It's 2 squared root of 2, right?
So 8.
The square root of 8 or 2 square root of 2.
Oh, yep.
However you want to think about it. Okay. So u to the 3/2, or 2 to the 3/2, 2 to the 3/2. We can think about that as, we can either do the square root first and then cube it, or we can cube it and take the square root.
Okay.
So I can think about this as the square root of 2 cubed, or I can think about this as the square root of 8.
Okay.
Either one works, right? This is equal to, square root of 2 times the square root of 2 is 2, but we had 3 of them, so that's with 1 square root of 2 remaining.
Yeah.
Square root of 8 is the same thing as the square root of 4, the square root of 2 squared times 2, right?
Mm-hmm.
Since I have 2 squared, I can pull a 2 outside using my square. So pulling the 2 out gives me 2, and we still had 1 2 inside. Good?
Yeah.
So this is 2 roots of 2 times 2 is going to be 4 square roots of 2 over 3. Minus what we get when we plug in 0, which is 0.
And that's your answer, right?
That's our answer.
Yep.
Remember, now we're calculating a definite integral. So it's going to be a number, not an equation.
Oh, and we don't need to go back to x because we changed.
Because we
that.
just cared about the number.
Yeah.
Now, we could have gone back to x, so let's see it that way. We could have said the integral is, so we could have left those off. We could have said the integral is just this thing. Drop this off for a second. Which is equal to 2/3 times x squared plus 1 to the 3/2, and
X
now we
cubed
evaluate.
plus 1.
Oh, thank you. X q plus 1. And now we evaluate this for a negative 1, 1, going back to our bounds of integration.
Okay.
When we do that, when we plug in 1, what do we get? 1 plus 1 is 2. 2 to the 3 halves is 2. Square root of 2 times 2 thirds gives me 4 square root of 2 over 3, right?
Mm-hmm.
Minus, what do we get when we plug in negative 1? 0.
3?
Sorry, what? Oh, I said 2, but I wrote 3, huh?
Yeah.
Thank you.
Okay.
Right? So it doesn't matter which way you do it. I personally like changing the bounds of integration, but
Okay.
whatever floats your boat. Alright, let's do another one. Alright, we're doing the integral from pi fourths to pi halves. Uh-oh, that means a trig function.
Yep.
And we're going to do cotangent of theta times cosecant squared of theta d theta. What should I let my u be? What should I let my du be? Well, just what should I let my u be? If you're not sure, throw out a guess, and we'll just play with it.
Cosecant squared.
Cosecant squared.
Mm-hmm.
So if I do u is equal to cosecant squared of theta, what's my du going to be? We're going to have to do the derivative of the first multiplied by the second plus the derivative of the second multiplied by the first. The derivative of cosecant is cosecant times tangent. So we're going to get 2 cosecant squared times tangent.
Isn't it negative tangent?
Now,
Oh, you're right. No.
cosecant squared of theta times tangent of theta. D theta would be our du. Is that helping us?
Not really.
Okay, so probably a bad guess.
Okay.
Cotangent.
Cotangent, kind of the only other option, right? Cotangent of theta. Oh, what's du going to equal then? Oh, it's going to equal cosecant squared of theta d theta negative.
Oh.
Oh, so we see that in going and replacing this one, we just need to add a negative. So this is equal to negative the integral of u du.
Yeah. Okay.
Yeah.
And then we change our bound.
Change our bounds. When we plug in pi fourths to cotangent, what do we get?
What is cotangent of pi force?
What is cotangent of pi fourths? So let's remember what cotangent is.
Okay.
Cotangent of theta is equal to,
What is it? Something over cosecant.
huh? X over y, but what's x in terms of trig functions?
X is, there's cosecant and then there's
What gives you the x coordinate?
Cosine?
Cosine.
Cosine.
Cotangent is cosine of theta over sine of theta. Tangent is sine over cosine. Cotangent is cosine over sine.
Okay.
So, now we're looking for cotangent of pi fourths. What do we get?
of pi force.
Uh-huh.
Root 2 over 2 over root 2 over 2,
Yeah.
which is 2 over.
Okay.
Which is 1.
1. The same thing over the same thing.
Yeah.
Okay, so this becomes a 1. And then what happens when we plug in pi halves?
You get 0.
0. See that?
Yeah.
Okay. So now we can integrate.
Okay.
And we can calculate this. What's the integral of u? Well, don't forget our negative.
It's negative u squared over 2.
Perfect. We're going to evaluate this from 1 to 0. What do we get when we plug in 0?
0.
So we got negative 0 minus, what do we get when we plug in 1?
Okay.
1/2.
Negative 1/2, so it becomes
Plus
plus
1/2.
1/2, right?
Okay.
So this is supposed to have the bigger one on top of the integral.
Do not change the order. It's when you plug in the top minus when you plug in the bottom. The fact that the bounds flip is the bounds flip.
Okay.
The math is taking care of everything for you already. And the fact that we flipped it was accounted for with that negative there. And it was just working out itself. So you didn't need to change anything. Make sense?
Yeah.
Okay. And 1/2, that's what they got. Okay. Now they want to find the derivative, or the integral of tangent. And notice that a derivative of a trig function doesn't give us tangent. So we're kind of stuck. What are our bounds? Negative pi fourths to pi fourths. You don't know how to do logs.
Did last year.
The bounds will end up, okay. We can figure it out with what you know. The author's being a little tricky. Anyways, tangent of theta. Okay, we're stuck, right?
Yeah.
We have no clue what to do. Well, what is tangent of theta?
It's sine over cosine.
So maybe that will help us go forward. So let's rewrite it as sine of theta over cosine of theta and see if we are still stuck.
Okay, just make u be cosine of theta.
So if we do u is cosine of theta, let's do u.
Sine of theta.
What's the derivative of cosine?
Negative.
Negative
Sine of theta.
Okay.
D theta, right?
Mm-hmm.
So when we substitute in for d theta, we're going to get a negative. So this is equal to negative du over u. Follow that?
Yeah.
Good? What are our bounds of integration? Sorry, how do our bounds change?
Oh.
Negative pi fourths. Cosine is, it's positive root 2 over 2.
Okay. And the top one?
Same thing.
Same thing. Okay.
Isn't the same thing just always equal to 1 though?
No.
0.
0. So this thing is equal to 0.
Oh.
So if you see that, yep, we could have said this is equal to 0. But let's say you didn't notice that and keep trying with the sink.
Okay.
So we'll pull out the negative. So this is negative. Let's pull out negative. Negative the integral from the square root of 2 to 2, square root of 2 to 2. And we have u down here is u to the negative 1 times du, right?
Mm-hmm.
Okay. What is the antiderivative of u to the negative 1?
1.
0.
Is it 1 or 0?
I think it's 1. U to the 0 is 1.
Oh,
So you're saying that this is equal to
yes.
U to the 1 over 1, which is 1.
u to the
Oh,
1.
u to the 0 over.
You're saying it's u to the 0.
Oh, over 0. So you are right. It is 0.
Because when you divide by 0, you get 0, right?
Oh, it's undefined.
Okay, so here's where you're stuck. When I give you an integral like this, the integral of 1 over x dx, what does that equal? You don't know. This is the one place where our chain rule doesn't work. It is not equal to x to the 0 over 0, because that's undefined.
Okay.
And 1 to the x, that's a perfectly fine function. We can find areas under that curve. So it turns out this is equal to natural log of x. And there's no reason that you should know that. That's what we cover in chapter 7, which is a Calc 2 topic. So Calc 2 to start with this discussion. So you didn't know how to do this, so the only way to figure it out is, oh, it has to be 0 since top and bottom, since we're talking about the area under a single point. That's how the author expected you to get this.
Oh, so we did do it right.
So you did it right, but be careful. Just keep note of that, because I wouldn't have expected the author to give you a problem like this, where you don't know how to calculate the integral, but you were just supposed to look at the bounds to realize it was 0.
Okay.
So that was a little tricky of them. That's what I said. looking at that, you guys don't know how to do natural logs yet. Okay. Other tricky things to know. If a function is even, do you remember what an even function is?
No.
It's
Intuitively, what do we know about even functions? Do you have an example of an even function in your head that you think of when I say even function?
isn't it when it's like symmetrical on the y-axis?
Symmetrical with the y-axis.
Yeah.
And any polynomial, or any term, if you raise it to an even power, gives you an even function. If I take x and I raise it to an even number, I get an even function. If I take x and raise it to an odd number, I get an odd function.
Okay.
Now, not every odd function is x to an odd number, and not every even function is x to an even number, but that's how the names first came about.
Okay.
So x squared is even, x to the 4 is even, x to the 6 is even. X is odd, x cubed is odd, x to the 5 is odd.
Yeah.
So not all of your even functions, but a lot of your even functions, as examples of even functions, are things that look like this. And a lot of your odd functions are things that look like this. That was terrible, but hopefully you sound get the picture. All your odds look something like that, all your evens look something like this. Now with all your evens, if we were calculating an integral from negative a to a, how does the area over here compare with the area over here?
It's the same area.
It's the same. So if your function is even, then the integral from negative a to a of f of x dx is equal to 2 times the integral from 0 to a of f of x dx. The area from negative a to a is the same as the area from 0 to a doubled.
Okay.
What's the test for an even function? Do you remember that? If f of negative x is equal to f of x, it's even. If the height at the negative and positive x's give you the same height, always, it's even. It's symmetric with the y-axis. We're saying negative 2 and 2 give you the same height. Negative 3 and 3 give you the same height.
Okay.
Appeal to your intuition a little bit?
Yeah.
Odd functions. Let's look at an odd function from negative a to a, looking at the integral. If we go to negative a, that's the area here, right?
Mm-hmm.
If we go to positive a, sorry, my picture's lying a lot, but you get the idea. That's the area here. How does this area compare with that area?
They're the same.
They cancel out.
They're the same, but they cancel out. The same, but opposite.
Yeah.
So what's the integral going to be? If I know that from negative a to a, if I know that f is odd, what's the integral going to equal?
0.
0. Okay?
Okay.
What's our test for an odd function?
F of negative x equals negative f of x.
Perfect. F of negative x equals negative f of x. If I plug in the negative of x, I get the exact same height as I got at x, just in the opposite direction.
Yeah.
So if 2 gives me 4, negative 2 gives me negative 4. Make sense?
Mm-hmm.
So even and odd functions some nice tricks about them. So let's put a little bit of this into action and use some of it.
So we can automatically know what an integral will be just based off of whether it's even or odd?
Depending on the bounds. Remember, those have very special bounds. We were always looking at from negative a to a.
Oh, that's right.
So the bounds are very, very important in this case. So when you have symmetric bounds, you can start looking for other symmetries, like if it's even or odd. So, example, we're looking at the integral from negative 2 to 2. Okay, now you see, okay, maybe we can use one of those tricks.
Okay.
Of x to the 4 minus 4x squared plus 6. dx. Okay, and you're probably tempted to think that thing's even, right?
Yeah.
Plug in negative x, what do we get?
Negative x?
Yeah.
Oh.
So if f of x is equal to this thing, if f of x is equal to x to the 4 minus 4x squared plus 6, what does f to the negative x equal?
X to the 4 minus 4x squared plus 6.
Same thing.
Same thing.
So notice, since all our x terms are to an even power, it's even. Easy way to check.
Yeah.
And so, yep, it's even, which means we can rewrite this as the integral, as two integrals from 0 to 2 of x to the 4 minus 4x squared plus 6. Now, why is that useful?
Yeah.
We always like when there's a 0 in there, because plugging in 0 is real easy. That's the nice part of it. That's the work you're saving yourself. It's easier to plug in 0 than a -2 is a general rule.
That makes sense.
So that's why it's useful. Okay, so now this is equal to 2. Let's calculate the integral. The integral of x to the 4 is?
X to 5 over 5.
X to the 5 over 5 minus
4x to 3 over 3 plus 6x.
evaluated from 0 to 2. And this is equal to 2 times, notice that when we plug in 0, we just get 0. So we only have to worry about plugging in 2. That was a nice part. So 2 times 2 to the 5 is?
32 over 5.
32 over 5 minus, what do we have here?
32
32 over 3 plus 12. Which is equal to, let's see, we're going to have multiply this top and bottom by 3, multiply this top and bottom by 5, and multiply this by 15, top and bottom, right?
Yeah.
So, when we multiply this one top and bottom by 3, we're going to have 3 32s, and we're going to minus 5 of those 32s, and we're going to be left with -2 32s. You see that?
Which is?
Let me write that out just to make sure, because this is a common way to think about these before you go crazy doing all your multiplying out. I have 3 32s minus 5 32s plus 15 times 12. 15 times 12, whatever that is, we'll come back to that. All over 15, right? Which is equal to, now I have 3 32s minus 5 32s leaves me how many 32s?
-2.
-2 32s, so that's going to be -64. So I'm going to do 12 times 15 minus 64.
Okay.
Alright, so let's see. Every 4 15s gives me
60.
60, so this is 3 60s.
So 180.
180. So we're doing 180 minus what?
64.
64 over 15, and don't forget our 2 times it, right? So 180 minus 64, what does that leave me with?
116.
116, now times it by 2.
232 over 15.
And let's see what they get. 232 over 15, perfect. Okay. Feel like we got a pretty good grasp on these things?
Yeah, I just feel like we just need to do them ourselves.
Yeah, a bunch of examples. So I think the last thing we're going to be talking about is now calculating the area between two curves.
Between two curves.
Between two curves.
Okay.
So if I've got some function, here's A, here's B, and one curve looks like this, and the other curve looks like this. Now I want to find the area between these curves. I want to find this area. How do we do that? Let's think about our Riemann sums for a second, and I think it will pop out at us.
Riemann sums. What's
Riemann
that?
sums are rectangles.
Okay.
Let's think about our rectangles. So we're going to be looking at, this is going to be the sum from k equals 1 to n of what is our height of each rectangle going to be. Let's call this top function, we'll call this f of x, and we'll call this bottom function, we'll call it g of x.
F of x minus g of x.
F of x minus g of x is going to be the height of our rectangle.
Can you explain that?
F of c sub k, yeah, minus g of c sub k. And then the width of our rectangles doesn't change.
Yeah,
so it's
h
just still
would be-
delta x sub k. So it's just the height that changes in this formula. How do we get the distance from this point to this point?
Okay.
You subtract it. Now you do the absolute value of the difference, but if you always do the top function minus the bottom function, then it's already giving you the absolute value.
Okay.
Make sense?
Mm-hmm.
So if you keep in track in your head which function's on top, which function's on bottom, then you can just do their difference.
Gotcha.
If you just want a generic formula, you need to take the absolute value. But when you take the absolute value, in practice when you go to calculate that, you gotta figure out which one's on top. So it comes down to doing that anyways. Okay? So that's the only thing that changes in our whole formula. So if I want to find the area between these two curves on A and B, it's just going to be the integral from A to B of f of x minus g of x, assuming f of x is on top, all times dx, the width.
Well, that makes sense.
So pretty straightforward, right?
Mm-hmm.
Okay, so let's write out one of their examples and find the area. Oftentimes with these area ones, it helps to do a quick sketch of the problem and see exactly what you're talking about. So I strongly recommend that. So the area of the region enclosed by the parabola y equals 2 minus x squared and the line y equals negative x. So let's draw a rough picture and see if we can read the problem again and make sense of it.
Okay.
Because so far you might be confused what exactly that's asking. Draw a picture. So 2 minus x squared, that's going to be up here. Here's 2. Where does this cross the x-axis? At the square root of 2, which is somewhere like right there. So this is a parabola pointing down like this. Okay?
Why does it cross at root 2?
Where is that 0?
Oh, that's right.
Plus or minus root 2. Negative x.
Okay.
Good? Now let's read the question again. Find the area of the region enclosed by the parabola y equals 2 minus x squared and the line y equals negative x. Find the area enclosed. What's the area enclosed? It's obviously this portion, right?
Mm-hmm.
So we need to integrate our top function minus our bottom function, starting here and ending here, wherever those points are.
Okay.
So we got to figure out those points. How do you figure out where two functions intersect?
Oh,
You see where they have the same value,
okay.
right?
Yeah.
So I want to know where, for the same x's, they give me the same y's. So I want to know where this function is equal to this function. I want to know where negative x is equal to 2 minus x squared.
Oh, I see.
Right? So, in other words, I want to know where I'm going to move these terms over here and just leave a 0 over here.
You're going to move everything? Why not leave it 2?
Because it's easier to factor. X squared minus x minus 2 equal to 0. You always write it like you just have 0 over there. Because worst case scenario, now I can use a quadratic equation. Okay, but this one's easy enough to factor. So this is what?
X minus 2.
X plus 1.
X plus 1.
So I know at negative 2, sorry, at positive 2 and at negative 1 is where these intersections are. So my picture's lying.
Okay.
So this point right here is happening at -1, so here's -1, even though my picture's lying. And this point right here, here's 2, even though my picture's lying.
Okay.
You with me?
Yeah.
So we know that we're doing the integral from -1 to 2. Remember your left-hand point to your right-hand point. Make sure you put it in the right order. Of our top function minus our bottom function. Of 2 minus x squared minus x plus x, because we're going to minus that.
Yeah.
dx.
Yeah.
And now it's trivial to figure it out. So the hard part of these is to go from the area we're talking about to your integral. Once you have your integral set up, now it's just math.
Okay.
And it becomes stupid easy, right?
Mm-hmm.
So now, take the integral, what do we get?
2x minus x cubed over 3 plus
What do we get when we plug in 2? We're going to get 4 minus 8 thirds plus 2, right?
Mm-hmm.
So, may as well get it all in terms of thirds, because I assume we'll have thirds in our second term as well.
It's just 10 thirds.
It's just 10 thirds.
Yeah.
That's 6.
6 times 3, 18. Good. 10 thirds. And now, for our next one, so that's this term, minus, what do we get when we plug in -1? We get minus 2 plus 1/3
Mm-hmm.
minus a half, plus a half.
Plus 1.
So, let's see, a third plus a half is 5/6. So we have 5/6 minus 12/6, right?
Yeah.
So minus -7/6 gives us plus 7/6, right?
Mm-hmm.
Yeah.
So this whole thing is going to be equal to what?
27/6.
27/6. Hopefully. Let's see if we did that right. Oh, yeah, threes go out. Which, 9/2. That's what we got. So we did it right.
Yeah.
Okay.
Okay, next one. Another find the area problem. No, we just did that one. Not this one. Find the area of the region in the first quadrant. You know what the first quadrant is, right?
Mm-hmm.
Yeah.
Okay. Find the area in the region in the first quadrant that is bounded above by y equals the square root of x and below by x minus 2. Y equals x minus 2. So I have y equals square root of x. I have y equals x minus 2. Yeah, I said that right. And we're talking about the area between these curves in just the first quadrant.
Okay.
Okay.
So we're only looking at the first quadrant. We don't care about anything else.
Mm-hmm.
Try and draw a slightly better picture this time. Let's go all the way to 4. Okay, so I'll start by drawing my square root. Square root of 1 is 1. Square root of 4 is 2. Right?
Yep.
So our square root function was rough, still terrible.
It works.
Still terrible. Can't. That is awful. Let me draw it this way. It's going to be more like, no, I lost my point I was going to over here. It's going to be more like that. Slightly better. Okay, and then x minus 2, that is going to be, its y-intercept is down here at -2. By the time it gets up here, so it's going to come in right here. It's going to go up and over for 3, and then up and over for 4. Okay, so we know where they intersect. Right out the door. But in case you didn't want to trust your picture, maybe you thought you made a mistake, you can check really quick. Where does x minus 2 equal the square root of x? Move everything over so that we just have 0, so we have
Yeah.
x minus the square root of x minus 2 is equal to 0. And let's factor this. Square root of x, square root of x equals 0.
-2 plus 1.
Plus 1. So it's where the square root of x is equal to -1. That never happens. Or where the square root of x is equal to 2. Or in other words, x is equal to 4.
Yep.
Okay, so you can check it either way. Which means, by the way, that these don't intersect again. They only intersect once. Square root function just starts right here. You can't take the square root of negative numbers.
Yeah.
Okay. Anyways, so we're looking for this area, right?
Mm-hmm.
Now, we got to be a little bit careful because over here, we're not doing the top function minus the bottom function, right? If we did the top function minus the bottom function, that would give us all the area all the way down to here.
Yeah.
We only want that portion of it.
So until it gets to that point, it's just f of x.
Perfect. So from this point to this point, this portion of the area is just the integral from 0 to 2 of the square root of x dx. That gets us this portion. Oftentimes you need to break these up into multiple integrals, is the point.
I see.
There isn't necessarily one integral that just gives you the answer. So then we got to do plus the integral from 2 to 4 of the square root of x minus x minus 2.
dx.
Something like that. You follow me?
Yeah.
Okay, and then from here on out, it's really easy. So this is equal to, what's the integral of x to the 1/2?
2/3 to the x to the 3/2.
We're going to evaluate that from 0 to 2,
Mm-hmm.
plus,
Same thing. Minus.
parentheses here,
X squared over 2 minus 2x.
plus.
Plus 2x, yep.
And this is evaluated from 2 to 4. Follow, sir?
Mm-hmm.
Okay, so now let's just evaluate it. This is equal to, obviously when we plug in 0 we get nothing, but when we plug in 2, what do we get?
2 times root 2 over 3.
4 root 2 over 3.
Oh, yeah, that's right.
Because this by itself, when we plug in 2, is 2 root 2.
Mm-hmm.
And then times 2 gives us 4. Okay. And then minus the 0 still leaves with this. Okay, plus, let's see, what do we get when we plug in 4? So plug in 4 here. What's the square root of 4?
2,
Cubed
8,
times 2.
16,
We have 16/3 minus
8
6,
plus 8.
plus.
So just 16/3.
Here, let me do square brackets here. And then we'll do round brackets. This was plugging into 4, and we got minus what we get when we plug into 2.
Oh,
Right? Don't forget. Minus, when we plug in 2 to that, what do we get?
4 root 2 over 3,
mm-hmm.
2, minus 2, plus 4.
Okay. So that's what we've got to figure out. So this is equal to 4 square root of 2 over 3 plus
16/3
16/3
minus 4 root 2 over 3.
minus 2 plus 4 square root of 2. Oh, 6. If we make it all over 3. Right?
But you could just take out the 4 root 2 over 3 with the 4 root 2 over 3.
Yeah, the 2 4 roots over 3
Because that
cancel
one's a
out.
negative, the other one's a positive.
Oh, you're saying with this?
Yeah.
Okay. Yep, that's a good idea. So minus 4 square root of 2 over 3, and then we
2.
have minus 2,
Oh, yeah,
which is now equal to, okay, so that goes out with that. 16 minus 6 is 10/3.
Yep.
Where's the answer? 10/3.
Nice.
Okay. Now, let's do another one. We're going to do the same problem. And this time we're going to do the same problem, but we're going to solve it with one integral.
What?
I know, right?
Okay.
Instead of thinking about this in terms of, instead of thinking about my rectangles as having a delta x times the height, I'm going to think about the base of my rectangles being the y, and using this as my height.
So you're just switching stuff around?
Yeah, so instead of thinking about y is a function in terms of x, I'm instead going to think about x is a function in terms of y.
Okay.
So instead of thinking about this function as y equals the square root of x and y equals x minus 2, I'm going to think about this function as x equals y squared from this one, solving for x.
Why not root y?
Square both sides.
Oh, I see what you're doing. Okay.
And solve this one for x, and we get x is equal to y plus 2.
Yeah.
Right?
Hmm.
So now, when I calculate my integral, if I'm doing a bunch of delta y's, I'm going now from 0 to 2.
Okay.
0 to 2. What is my height? What is this height?
2.
It's this function, I'm saying anywhere.
Oh.
It's this function in terms of x, or in terms of y, minus this function in terms of y.
Okay.
So this one's the top one, this one's the bottom one. So it is y plus 2 minus y squared dy, which is our base. Base times height. We're thinking about our rectangles this way now.
Mm-hmm.
Does that make sense?
Yeah.
And then we can calculate this all in one go. So sometimes you can be a little bit tricky with it.
Okay.
So this is equal to, let's just rewrite it really quick, 0 to 2. Oh, we don't need to. I have some simplifying to do. We can just calculate it. What's the integral of y?
2y, y squared plus, and then plus 2 again.
Evaluated from 0 to 2.
Mm-hmm.
Makes no difference. And so once again, when we plug in 2, what do we get?
2 plus 4 minus 8 thirds.
Which is going to be 18 minus 8,
10 thirds.
10 thirds. Because the 0 is a 0. See how much easier that was?
So it's useful for situations like this.
Yes, so you can rethink in terms of, what about if I think about this over here is the base of my triangles, my rectangles, and my height this way. And you can think about that way.
Okay.
And we know how to get this distance. How do I get the distance from here to here? I do x at this point minus x at this point. What is x at this point? Y plus 2. What is x at this point? Y squared.
I see.
Make sense?
Mm-hmm.
So think about whichever way you think helps the problem along. Now, a lot of students are so in love with x's and y's being used the way that they are that this is so hard for them that they'd rather split it up into 2 and do all the extra algebra.
Yeah.
I strongly recommend trying to train yourself, when you can, to think about it in terms of y. Because in the next section, there's going to be places where you don't have a choice in the next chapter. Okay. So always see if you can do it in terms of y. Not always see, but if it looks like it makes sense to do it in terms of y, give it a go. See if you can do it. Try and force your brain to make that switch.
Okay.
And even if you need to regraph it, so that you call this your y-axis, this your x-axis, and redraw it, if that helps you, do it. Because we can do that, right? I can replot these things, calling this my y-axis and this my x-axis.
Yeah.
Let me just do that really quick, just to make sure that we're all on the exact same page here. Okay, so if we regraph this thing out, what are we talking about? So I have y equals x squared, or x equals y squared. This is my y-axis now, and this is my x-axis. So let's put some points in here. Let's graph this. When y is 1, x is 1. When y is 2, x is 4. Right?
Yeah.
That is this curve. And now we have x is equal to y plus 2. The x-intercept is 2. And now we get a slope of 1.
Oh, I see.
And we're calculating this area. That area, you know how to do. That's the integral from 0 to 2 of the top function minus the bottom function. Our top function is y plus 2. Our bottom function is y squared. Exact same thing.
I see it. Yep.
Okay. So, if this helps you, go through the pains and do it. Because making this paradigm shift, being able to like see in your head, review this thing now as a function in terms of y, just have a function in terms of x, that is so useful for so many problems going forward. It will help you out so much in life.
Okay.
Because I know you're both going to go on to get real degrees, right? And real degrees is going to help. You know what a real degree is?
A real degree.
Yeah.
Lots of work.
Not necessarily a lot of work, but requires you to at least learn.
Yeah.
Because there's two types of work. There's the work that causes you to grow, and then there's busy work. So I tell you to count to 1 trillion, that's a lot of work. Doesn't do you a lot good, though. So now, a hard degree doesn't magically make it a good degree. But if it's a good degree, it's going to be hard. Because it takes work to learn, but just because you're working doesn't mean you're learning. Right?
Yeah.
Okay, so we did that, we did that. Last example, and then we'll be done. Told you this was nothing new, just a bunch of new types of problems, right?
Yeah.
So we're finding the area of the region bounded by the line y equals 2 minus x, and y equals square root, no, that's the whole thing put together right there. Square root of 2x minus x squared minus x squared. Okay?
Okay.
Does it give us a quadrant?
No, just bound between these two curves. So these two curves are going to intersect at 2 points.
Okay.
So get a rough idea for what's going on here. First off, y equals 2 minus x. We know exactly what that looks like, right?
Yeah.
Mm-hmm.
That just goes like this. I know I don't need to go to negatives because I know I can't do negatives. Oh, maybe I could plug some negative numbers into there. So maybe I do need to go this way some. I definitely don't need to go below the x-axis because I can't take a square root and get something negative.
Yeah.
So that's why I'm cutting off my picture a little. That's that one. Let's go ahead and plug 0 into this. What do we get?
0.
0.
If you plug in 1, you get 1.
If we plug in 1, we get 1. If we plug in 2, what do we get?
You get 0.
We get 0.
Oh, what the
So this is going to
Close.
curve like this, I bet. I'm not sure.
It's so small.
heck? So it's kind of like the sine function.
It's going to be a teeny area, right?
Yeah.
Let's pick a number really quick. Right, like right here, 3/2. Let's see which of these is on top.
Okay.
So when I plug in 3/2 to that, what do I get?
1
1/2.
Or
When I plug in 3/2 to this, what do I get? I get 3 minus 9/4
you get negative
squared.
root.
Huh?
Oh,
12 minus 9, this is the square root of 3/4. Okay, is the
Right.
square root of 3/4 greater than 1/2?
I have no idea. I don't think so.
How can we make that make sense? I think it is. Well, I know it is. But I'm trying to find good intuition for it. What's the square root of 1/4?
1/8.
What times what gives me 1/4?
1/2.
Oh, 1/2.
So 3/4 has got to go up.
Okay.
That's right.
Okay, so there's intuition.
Okay.
Okay, so we know that this function is on top for some portion here and then goes back under. So we're finding this teeny area. We need to figure out where it intersects. We know it intersects at 2. So I know I'm doing the integral from something to 2. 2 is my ending spot.
Mm-hmm.
I don't know my start spot yet. Of this minus this. Right? Okay, so now we need to figure out where these functions intersect.
Okay.
So I need to know where 2 minus x is equal to the square root of 2x minus x squared. So square both sides, what do we get? We get 4 minus 4x plus x squared is equal to 2x minus x squared. Did I do that right?
Mm-hmm.
Now I'll move all our terms over here and leave a 0 over there. So we'll have x squared, and this will be adding x squareds to both sides, so we'll end up with 2x squareds
Minus 6x
minus 6x
plus 4.
plus 4 is equal to 0. Divide both sides by 2. X squared minus 3x plus 2 is equal to 0. So we're going to get x minus 2 minus 1. Yeah.
Yeah.
So when x is 1, they're equal. What did we get when we plugged 1 into that?
You got 1. Or. Yeah.
Yeah, it should.
Picture's just like.
Oh. Okay. How absurd. You shouldn't have taken us that long to figure that out. 1 to 2. Now we gotta calculate our integral.
Mm-hmm.
Uh-oh, we're in trouble.
Do the u thing, yeah, substitute u. U is equal to 2x minus x squared.
So if I do u is equal to 2x minus x squared, du is equal to negative 2x plus 2
Yeah.
dx.
Does that work?
Not great,
You still have
because
the
that's
number
not
of x.
multiple. Yeah, it's not multiplied to anything. Well, should we try it in terms of y and see if it's something more workable?
Why not?
So we know in y it's 0 to 1, so we know our bounds of integration, so I'm going to rewrite this in terms of y and see if it's a more workable integral. Understand what I'm saying?
Mm-hmm.
So 0 to 1,
Still end up.
our top function is still going to be this one, right?
Yeah.
And this is going to be our bottom function, but we need to solve these for x. So let's solve these for x and figure out what they are. So when we solve this one for x, what do we get?
Y
We
minus 2.
get x is equal to, we'll swap those.
Oh, that's right.
And here, we'll get, let's see, we have y squared. Oh, we're not going to be able to easily solve that for x. Okay, that's not helping either. Let's see, y equals that, y squared equals that. Solving for x. Oh, that is how he's doing it. Alright, we'll keep going with it. So y squared is equal to 2x minus x squared. So, the square and write it as a perfect square, yes? So when we complete the square by this, we take that divided by 2, square it. So plus 1 and minus 1. We're completing the square, so we're going to have y squared is equal to, let's factor out a negative, negative x squared minus 2x, let's see which one do I want inside, minus 1, and then we have, that's actually plus 1, so we have minus 1 outside. Okay. You with me so far?
Yeah.
Okay, so all the algebra is good. So now, we can rewrite this as, so now that that's a perfect square, I need more space to write without erasing a picture. Oh, we're not going to be using any of this anyways. Okay. So we found our first x, what x equals. Here we had y squared is equal to negative x minus 1 squared minus 1.
Yeah.
So, move the negative over, move the 1 over. We get 1 minus y squared is equal to x minus 1 squared.
Square both sides.
Take square to both sides. So we get the square root of 1 minus y squared is equal to x minus 1. So we get x is equal to the square root 1 minus y squared plus 1. Okay, so that's our top function, and here's our bottom function still.
Okay.
Okay, so now we're doing the integral from 0 to 1 of top function, parentheses, top function square root of 1 minus y squared plus 1 minus our bottom function, that one, minus 2 plus y. Right?
Okay.
Y.
Isn't that a minus y?
It's minus here, but we're subtracting the top from the bottom. And so this is equal to the integral from 0 to 1 of the square root of 1 minus y squared. I'll write my plus y next. And then we have a minus 1 dy. But when I do my substitution, we get the same thing. Maybe I should have looked down further. Conclusion. Whether you try to use it using the x's or the y's, we don't know yet how to calculate this integral. So you can't do all of them. That was literally the point of the example. If you do it with x's, you get stuck. If you do it with y's, you get stuck. That's literally what you're doing with the example. Okay.
Well, that's kind of
So
stupid.
the world makes sense again. So that's the last example. You have the rest of the class to start on homework problems.
Yeah.
Stop the recording.